All right, so in this video, we're going to be looking at the properties of summation notation. And so we're going to go through some examples of things that you can do and things that you can't do with summation notation. Now, we're not going to be looking at like summation formulas or anything like that in this video. That's in another video, but we are just going to be looking at how to manipulate summations. So let's start with a really simple example just to define what we're talking about, and then we'll go from there. So typically, a summation notation has this capital sigma. This is not an E in Greek. This is an S. This is a capital S for summation. And typically at the bottom, we will start with an index. So I, N, J, K, these are all pretty common indices. I stands for index. Sometimes N will get used as the number. But in this case, we're going to use I for the index as our counting parameter and N as our stopping point. And then typically there'll be some kind of an expression inside our summation that tells us what it is that we're counting and for how long. So this is the standard kind of format. And I guess in general, we could call this function of I, because we often have more than just I in the expression. We have some kind of expression in terms of I. So let's start with just what does this mean? So if I put in some specific numbers, I equals 1 to 5, let's just say I to start with, then what we're going to be adding up is we're going to start with I equals 1, and then the summation says keep adding, add all these terms together. So then I equals 2, and then 3, and then 4, and then when we get to 5, we stop. So in this particular case, we're going to end up with, let's see, these together is 9, that makes 10, that makes 15 altogether. So we're just writing this out like so. Again, it's just a shorthand for we have to do a bunch of additions. So let's say I started with I equals 1 to 5 of, and again, the stopping number can be different, 2I minus 1. So now this is a little bit more complicated, but the procedure is still basically the same. We're going to start with I equals 1, and we're going to plug it into our formula, and then we're going to keep doing that and then add up all the results. So when I is 1, this is going to be 2 minus 1. And then when I is 2, this is going to be 4 minus 1. And when I is 3, this is going to be 6 minus 1. Oops. 6 minus 1. And then when I is 4, this will be 8 minus 1. And then when I is 5, which is our stopping point, that'll be 10 minus 1. And so what we've got here is 1 plus 3 plus 5 plus 7 plus 9, which is going to give us 25. Now, because we're just adding, we can do things to our summation notation that we can do with other kinds of addition expressions. So I have this summation of 2I minus 1. You can see from this expression that this is going to be equivalent to I equals 1 to 5, whatever the stopping point is, 2I, minus the sum of I equals 1 to n of 1. Because notice that if I just rearrange these additions, I can take my minus 1 and my minus 1 and my minus 1 and my minus 1 and my minus 1. I have 5 minus 1s. I can collect them together. And I can just say each time I have an index, I put on another -1. It doesn't change. It's just always -1. I end up with 5 of them, and I can put them together. And then all these other terms, 2i when I is 1, 2i when I is 2, 2i when I is 3, 2i when I was 4, 2i when I was 5. I can put those together in their own summation. And the other thing that I can do is I can, because this 2 is multiplying 1 plus 2 plus 3 plus 4 plus 5, just a sum, I can use my distributive rule and I can pull the 2 outside. So this will become 2i equals 1 to n of I minus the sum of I equals 1. Well, these are all 5s. I should, since I'm using my previous example, of 1. So I can do these algebraic manipulations because this is just a sum. And since I'm adding things up, anything that I can do to a string of written out summations, I can do to a summation notation. Now, things that I can't do to a string of sums is like distribute powers. So if I have a summation with a square around it, let's say, I can't just square every term because I can't do that. When I have x plus 3 quantities squared, I don't just get x squared plus 9. There's a middle term in there. So I can't do that. But when it's just constants, multiplication, regular distributive rule, I can do that. I can pull things apart and, but I can't do powers like that. So just, again, it's very tempting to try to do that. It's tempting with 2 terms. It's tempting with lots of terms, but it's still wrong. Now, the other thing that I can do is I can manipulate my indices. So suppose that I want to break up my summation. Let's say I want to go from I equals 1 to 20 of some formula. And again, I don't really care about the formula in this case because I'm going to worry about the indices. I can split this up into, let's say, I equals 1 to go to 10. And then I equals 11 to go to 20. Now, what that actually tells me, though, is that if I want this, I want to start at someplace other than 1, I can move this piece to the other side of the equation, and I can get a subtraction relationship for missing terms. Now, sometimes this can be very useful because I may want to start at a value other than 1, but typically my formulas that we have, again, covered in another video, for actually doing these without like literally adding up every single term, the formulas for these all start at 1. And so if you have a representation that is not started at 1, you're going to not have a hard time using the formulas. But if you remember this relationship, then you can rewrite your expression with terms that both begin at 1. So you add up all of the ones in this case to 20, and then you subtract off the ones you don't need, which are the ones between 1 and where right before your next sum starts. Now, one other thing that I want to bring up in here is resetting an index. So another strategy for doing this, like starting at a different value, is sometimes maybe you have a bunch of sums that you want to add them together. They're not all starting at the same index. So in order to actually add them together and combine them, you need to make them start at the same index. So in those examples, we want to look at what happens. Let's say I'm starting at I equals 2 to n. And again, I have just let's come up with some expression, I squared minus 2i, just to sort of make it concrete. Now, the way that you're going to have to do this essentially is you can think of this as, let's say I want to start at I equals 1 instead of I equals 2. So I'm going to say, instead of I equals 2, I'm going to replace that with k plus 1 equals 2. So what does that imply? That means I'm going to start at k equals 1. So let's start rewriting our summation based on this idea. So k equals 1. So again, another way of thinking about this, since I'm trying to get k to be, there's a relationship between k and I, this is equivalent to saying k plus 1 is equal to I. So that's k plus 1 equals 2 is the starting value. Now, if k plus 1 is equal to I, then that's going to imply that I is equal, so anywhere there's an I in my expression, I'm going to have to replace it with k plus 1. So notice I'm stepping down my index, which means everywhere in my expression, I have to step up my index value. So if I'm starting at k equals 1, what happens if I'm looking at my expression here? Well, everywhere I have a k and I, I'm going to have to replace it with k plus 1 inside my expression. So now I'm going to have to, boil this out and everything to get my new result. It won't just be k squared minus 2k. It's going to have other terms in it. The other thing to keep in mind is that if I'm starting one index lower, I'm going to have to stop one index sooner. And again, if your final value for the last term, in this old expression, you would plug in n. Here, if you plug in n minus 1 into k, you're still going to get n squared minus 2n. So it's always a good idea to sort of check your arithmetic as you're doing this, because this can be a little confusing. Here you step down in the indices, in the summation notation, but on the inside in the formula, you have to step up, you have to compensate. So it can seem like it's a little confusing, but if you switch out your index with another index variable, then it's a little easier to see how you're making these replacements and not getting them confused. And then, of course, you can always convert them back. Once you have this rewritten, you can always convert it back in terms of I, so that all of the other indices, all of the other summations that you're working with have the same index variable in them.